Okay, so good evening everyone.
Hi, good evening, Saish.
Good
Good evening,
evening.
everyone.
Okay, so are there any queries from the previous class or previous session?
We are fine. I am fine.
Okay. Akhilesh, I'll come to your query like how to save your the figures. Will plot some regression plots and then we'll try to see like how you can save it in your local system.
Yeah, please.
Sure. Okay. So let us do a brief recap of what we did in the last class, and then we'll move on to regression and certain terminologies relating to regression, and we'll solve some problems in Python. And we'll also try to solve some questions as well, the MCQ based questions that you might expect in your examination. Okay, so just want to
If,
confirm if my screen is visible to everyone.
if possible, can you explain how to solve the regression with the help of Excel also?
Excel. Okay, I
Yeah,
have not done that such, but definitely in the next session I can do that.
no
I,
issue.
yeah, I need to check it like how that can be done.
Well,
I've not used Excel much.
one of the video I think
Yeah, I think
professor has
professor
used.
has mentioned like explained that.
Yeah,
Yeah, I'll also look into it and then we'll explain it to you in the
please,
next session.
please.
Yeah, sure. Okay. So till now, like just a second, I'll mute everyone. Okay. So till now we have seen, so this is like week 6 slides. We'll move on to week 7 and then kind of like touch upon week 8 concepts. So week 6 we have seen two sample hypothesis testing like t tests and z test like with multiple conditions like when the population variances were known and population variances were not known, and then we moved on to testing hypothesis for multiple groups like we saw the drawbacks of t-test for multiple groups like when we have to compare the population means of multiple groups, and in that case we went on to ANOVA, and then in ANOVA we saw one way ANOVA where we had one independent variable, and then we moved on to randomized block design, got to know the importance of taking the block level information into consideration, and then after that we moved on to two-way ANOVA where two independent variables were taken into consideration. And then one thing that we saw about ANOVA was like it does not give you information about which means are different. It only tells you that uh, there is at least one pair of means which are different in the given groups. So to do that, like to find out which means are groups are different, you will have to do certain post hoc analysis on top of uh, the group data to identify the differences in them. Okay, so we saw certain problems as well on randomized bulk design. Like we just went through the problems that were solved in the class, and then we uh, did some Python programs to solve these things in Colab notebook. Okay, so after that we moved on to linear regression, and we kind of like touched upon it, and we'll discuss it in detail in today's session. Okay, so here are few questions, MCQ type questions. So we'll look into these questions and then we'll move on to regression, solve some problems like the MCQs on regression, and then we'll see how to do linear regression, how to solve linear regression in Python, and we may also solve like certain queries you may have relating to that. So let us begin. Okay, let me just stop the share and I'll share that particular tab. Okay, in that on that note, is there any query on whatever topics we have seen so far? Okay, there is one more thing like I wanted to share. Okay, it is relating to what Nikhil has asked in the previous session. So there were like different types of tests that we saw. One was one sample t test, uh, in which like we were comparing the given a group given a sample coming from a population, we were trying to see if the population mean is like if the population mean is having certain value or not. So for that we were doing one sample t test. Then we moved on to two samples, like to compare the population mean, population means of two samples. The means of two populations using samples from these two populations. So there were two conditions: either the two groups can be independent. Say group 1 is like school children, like height of school children, and then group 2 is like college students and their heights. So what is that, like, is there any significance difference between the heights of these two groups? So these are two independent groups, and we are taking samples from these independent groups and then trying to see if the difference in the mean is statistically significant or not. Now in this case the two groups were independent, but in certain scenario you may have a condition where the groups, you might be doing certain experiment on a single group. For example, you might be having certain diabetic patients, so you are kind of like measuring their blood sugar level before the test is like before the medication is done. Say they have certain blood sugar level, each one of them is having certain blood sugar level, and you provide them with certain medication and certain dietary restrictions, and then after 1 week you measure their blood sugar levels, and there will be certain difference in that. So what t-test is used for is to check the significance, like the difference between the initial condition, like before the medication was done and after the medication was done. Okay, so let us see this example over here. So I just found this online. So there are two groups, like there is a group of students, and by the way, this is not there, I think, in your syllabus. Paired t-test might not be there, this is just for your information. So exam 1 score. So there are some students who performed like who have certain scores for an examination, and then certain assessment, like certain tutorials were taken and so on, and then they appeared for another examination in which their scores changed. So there are like certain differences in the score. Some scored better than the previous examination and some scored worse. So we have to see how significant is the difference between the scores between these two conditions, like exam 1 scores and exam 2 score. One thing is, here there are not two independent groups. These scores are taken for each of the student before that particular tutorial or whatever classes were taken between these two particular examinations. Now the task is to see. So generally in two sample t-test, what we do, we take the difference of the sample means, like sample mean of mean of first sample and mean of second sample, and then we compute the standard error. But in that case also, like, we saw different conditions when the population standard deviations were known. So they in that case we went into z-test, how that was computed: x1 bar minus x2 bar divided by under root of sigma 1 square by n1 plus sigma 2 square by n2. That was the standard error in that case. Then we saw two conditions when population standard deviations were not known. In that case we were computing sample standard deviation, and then in that case one assumption was like the standard deviation or the variances of the two populations are the same, and in the other case we assumed the way standard deviations of the two populations were different. So in that like each case was having a different way of computing standard error and the degrees of freedom for the t-test. Okay, so in this case the statistic is defined as, so you have one group, you have a group, you have certain values, like let's say blood sugar level before medication was given, blood sugar level after medication was given, and difference in the blood sugar levels. Okay, so you want to see how much this difference, like how statistically significant these differences are. So it's simple. You have to compute the t statistic, and in this case t statistics is nothing but the average of the difference divided by the standard error, and average of the difference is the average of these differences computed over these two values, and standard error is nothing but the standard deviation of the differences divided by square root of n, where n is the sample size, the number of people in that group. Okay, so t statistic is average difference divided by standard error, and once you get the t value, the degrees of freedom is n minus 1 in this case, where n is the number of people or the sample size. So you will be computing the p value corresponding to this particular t value, and then based on the significance level you will accept or reject the null hypothesis. Is that clear to everyone? Nikhil, is it clear? Okay, just want to confirm, am I audible to everyone?
Yes, you are audible.
Okay, is there any query in the pair t test? So it's basically like what we did for t test. We had a sample, you computed the mean of the sample, and then we computed the standard error and then divided the mean by the standard error. It's nothing but the same, but only thing is these values are the differences, unlike in the one sample t test where the values were coming from some population. Here the values are differences between the groups, like the values before certain condition and values after certain condition. Okay, so it's the same thing, only difference is in the concept that is used. Like here the values are coming from a single group. Okay, so let us move on to some questions. Fine. So our hypothesis is rejected at the 5% level of significance. It will always be rejected at. We'll quickly do this and then we'll move on to linear regression and Python based programs. A hypothesis is rejected at the 5% level of significance. What will be the appropriate answer over here? Okay, one answer so far. What about the others? Okay, let us see this on iPad. So the question asks, I'm doing certain hypothesis testing, say let's say Z test, and the level of significance was given 5%, that is 0.05. Say it is one tail test that you are doing. So this is my alpha, which is 0.05, and we are saying that the hypothesis, the null hypothesis, is rejected at 5% level of significance, which means that the statistic, the t statistic or z statistic, whatever you are computing, is falling after this critical value. What is critical value? Here it will be Z alpha or T alpha and so on, like depending on the test you have. So your statistic is falling somewhere over here in the critical region, that is in the rejection region. So the options were, okay, let me go back to our the options. I'll paste this in chat. Will always be rejected at 1% level of significance, will always be accepted at the 1% level of significance, will never be tested at the 1% level of significance, and may be rejected or may not be rejected at 1% level of significance. So the statistics that you are computing might be lying anywhere over here in this region, and say, let's say this is 1% level, this area is 0.01. So your statistic might be lying over here or here. So if it is lying over here, it may not be rejected at 1% level of significance. If it is lying over here, it will be. So the correct answer is will may be rejected or not rejected at 1% level of significance. Is it clear to everyone? Any query in this question?
Can you repeat once again?
Okay. So we have been given alpha. Okay, let me erase this. We have been given alpha, the level of significance. It is 0.05, which is nothing but the area under the curve. Say we are considering one tail test. So for this alpha, there will be corresponding Z alpha in the case of Z test, or T alpha in the case of T test. So this is Z alpha, and the condition given is hypothesis is rejected, which means null hypothesis H0 is rejected, which means that whatever Z value you computed, x bar minus mu upon sigma by root n, this particular Z value is lying beyond this Z alpha in the critical region. So your Z value is lying somewhere over here. That's why the null hypothesis is getting rejected. Now Z value may lie anywhere over here in this region, right? So this is 0.05, and let us say this particular region, the blue color area, is 0.01. Now if your Z lies over here and the level of significance is 0.01, it is lying in the acceptance region, the Z value. So your null hypothesis will not be rejected in that case. But if your computed statistic lies beyond this blue color critical region, so in that case, your null hypothesis will be rejected. So the correct option over here is your null hypothesis may or may not be rejected at 1% level of significance if it is getting rejected at 5% level of significance. Is that clear, Akhileshji?
Yeah, that means we are changing the value of the significance.
Yeah, value of significance is
From
getting
5% to 1%.
Yes. So we saw in one of the sessions like how we can reduce or increase the type 1 error, type 2 error, right? So in that case, like we were trying to, when does the type 1 error occur? When we reject null hypothesis when it is true. So to avoid error or avoid that type 1 error or rejecting null hypothesis, we were trying to increase the confidence interval or like reduce the significance level. So once you reduce the significance level, the acceptance region grows, like it increases, and hence your chances of rejecting the null hypothesis decreases. So in this case, like if your level of significance is decreasing, if it is getting rejected at like 5% level of significance, it may or may not be rejected at 1%, depending on the statistic that you are computing. Okay, I hope it is clear to everyone. Please let me know if it is not. I'll explain it again. Okay, so let us move on to the next question. So the correct answer is may be rejected or may not be rejected. Okay, this we solved already. There is a link to the collab notebook, so you may refer to that. I'll be sharing this with all of you later. Okay, which of the following justifies an experimenter's choice of using randomized block design? To test the effect of a blocking variable on a dependent variable, to control unwanted effects of suspected nuisance variable, to assess the interaction between a blocking variable and an independent variable, all of the above, none of the above. Okay, you can put the answer in the chat. Or let me start a poll. Okay, one answer so far. What about the others? Why were we using randomized block design? Okay, what about the others? Did you get that? Okay, let me just go to the answer. So the answer is to control unwanted effects of a suspected nuisance variable. So in one of the examples in the earlier session, we saw an example for like randomized block design and how to solve that. So in that case, we saw there were 3 systems and 6 flight controller. Like there were 6 controllers, different controllers, 6 people, and each system for each system they were having certain fatigue level. So the problem was to see if these 3 systems are different from each other or not. So there were like system A, system B, system C. But here there is one more information that is getting added, that is the controller level information. In one-way ANOVA, wherein we were trying to see only the difference in the 3 groups irrespective of the values in the group, like say length of fishes for a particular species. So there were 3 species into consideration and you were having length of different fishes in that particular species. So you wanted to see, given the length of fishes, you wanted to see if the 3 groups are different or not, and the data was homogeneous. But in this case, like when you are having this controller level information, that is like for each controller you are having certain fatigue level for each of the systems. So you'll have to take that also into account while computing the significance between the groups. So that's why like we moved on to randomized block design. So one-way ANOVA is known as completely randomized design because you don't have any block level information in that. Whereas in randomized block design, you have a block level information and you try to remove that nuisance factor that is getting created because of the blocks over there. So
Okay. Sorry, Saish. Can you explain with the help of an example or something?
Example what we saw in the last class. Do you remember the flight controller examination example that we saw? Okay, let me go back to the slides by Professor Ramesh. Okay, so here is an example. Say you have three fishes, species of fishes, and you have been given only the length of those fishes. So one way ANOVA will be simply to test the difference in the groups, like if the three species are having different lengths. But now you have been given, so in this case this problem was air traffic controller stress test, wherein you had three systems which each of the controllers were using, and each controller was having certain fatigue level for each of the system. So unlike in the fish example of fishes, wherein the values were homogeneous, means like there was no as such relation of one particular fish and their lengths across the three groups. Here in this case you are having three systems and 6 controllers, and each controller is having certain fatigue level for each of this system. So this extra information is getting added over here. So to remove this particular the nuisance factor that is getting created due to this extra information, and check the irrespective of this particular factor, what is the difference between these three groups, because each particular controller might be having different response for each of these systems. So the data is not homogeneous over here. So to remove that information, we were removing this block level information. So here we were having this extra term, that is sum of squares due to block or variance due to in each of the blocks. So in the SSE computation you were using, okay, let me go over here, you were using SST minus sum of square due to treatment, that is due to this particular groups, and then also you were removing this sum of squares due to block, that is the variance in the block. So that particular information was also getting removed, and then we found that the F statistic was getting increased. Why? How do we compute the F statistics? It is basically sum of square due to treatment upon mean square error, or sum of squares due to error. So since sum of square due to error is decreasing, the F value was increasing, and the chances of your null hypothesis getting rejected were increasing. If it were just one way ANOVA, if you were to compute one way ANOVA on this data irrespective of the group, we saw it in the previous session in the Python program, that this particular for this particular configuration, one way ANOVA was accepting the null hypothesis that there is no difference in the three systems. But when we removed this block level information, we got to know that the three groups are actually different. So that
Okay,
is,
but how is F statistics calculated here?
F statistics is nothing but the ratio of the variance of the treatment and the error.
Error, okay.
Yeah.
Here the block variance is not taken into consideration, only the treatment
Yeah,
variance.
so block level variance is considered, is getting considered by in computation of the error. So here SSE is being computed as sum of square due to total minus sum of square due to treatment and sum of squares due to block. So if you divide this sum of squares with degree of freedom, you will end up getting the variance. That also we saw in the previous session.
Yeah.
Okay, they call it mean square, but mean square is nothing but variance over here. You are dividing sum of squares with degree of freedom, that is nothing but your variance, and ratio of two variance gives you an F statistic. Okay, so that is the reason. So let us go back to the question. Which of the following justifies an experimenter's choice of using randomized block design? So the answer is to control unwanted effects of a suspected nuisance variable, and in that case it was due to the flight controller, air traffic controller. Okay, and there is this example given. Then we moved on to two-way ANOVA, where we're trying to see the effect of two different independent variables, like how significant these two independent variables were in deciding whether like which were like significant for your CAT examination scores. So we saw this example as well in the previous session. Now we'll move on to linear regression. Oops, okay. So in the previous session we saw like what regression is. So can anyone tell why we use regression? Okay, so let me just quickly tell you. Does anyone want to answer? Well, what is the use of regression? We saw two applications. You have been given one independent.
Finding the best fit line problem.
Okay, but what do you do with that best fit line? Like given the data points, you find the best fit line.
Yeah.
Yeah, that is fine. But given the best fit line, what is the use of it?
We can find whether the data points are significant or not.
Not really. Means like okay, we'll see that.
Okay.
Okay, so given the
Basically, whether we can find the variability for the given points. If x and y are related like that.
yeah, so that is the point. If x and y are related, so we are trying to find the relation between x and y.
Yeah.
So let's say you have this independent variable TV ads, and the dependent variable is sales of a product. So for each of the TV ad, you are having certain cells. And so on. So if you try to fit in a line over here, this line is the best fit. Why best fit? We will see shortly. So given this line, you can see two things over here. The relationship between the independent variable and the dependent variable. Here in this case, the independent variable is TV ads and the dependent variable is sales of a product. So here you can see as the number of TV ads are increasing, the sales of a product are also increasing. Okay, disclaimer, this always does not imply like if there is any linear relationship increasing or decreasing between two variables, it doesn't imply always, I am saying always, it may or may not, increasing TV ads implying increasing sales. It is not always true. So we'll see it later in one of the questions. We will come across one question and I'll give you an example why this is the case. So if you see such a graph, it may not be always true. Okay, so in this case, let us forget about that. But in this case, what it is showing is as we are increasing the number of TV ads, as you are giving more and more advertisements, the sales of your product are increasing. So now let me say I don't know. So I have like given this 5 advertisement TV advertisement, given this data 5 sample points of TV ads and the corresponding sales product. I have fit a line on that. So I have the equation of line with me, y equal to mx plus c. Okay, in the lectures, Professor Ramesh has used b1 plus b0. Okay, so now there are two things. One is the relationship between x and y, like the independent variable and dependent variable, and then the second thing is like given a particular value of the independent variable, say 7 ads, you can see the corresponding cells that you might be having. So here you can kind of like forecast or predict the sales of product that you might get for a given number of TV ads with this relation. Okay, so it is all such kind of things or regression is used in linear like machine learning for weather forecasting and all. We'll see multiple regression later. This is simple linear regression with one independent variable. We'll move on to multiple independent variables and see how that can be used. Okay, so this is the use case of regression. Now the question was, suppose you are interested in the relationship between social media screen time and happiness. You survey 1000 people whose social media screen time ranges from 0 hours to 12 hours. You also measure their happiness index, say through an appropriate questionnaire, like you circulate a form and then kind of quantify the level of happiness in their happiness on a scale of 1 to 10. So is regression appropriate for this purpose and why?
Yes.
Yes. Okay. Answer is yes. And why?
We can actually find like a mean time where this actually affects the relationship or something like that.
Okay. Yeah. So that is
We can find the variability between how this social media screen and relationship. Uh,
basically you are trying to find the relationship between the
yeah,
number of hours spent on social media and the
happens.
happiness. So
Yes,
here the independent variable is the number of time you the amount of time you are spending
spending
on
on screen.
social on screen or social media. So okay, let me come back to iPad. Okay, so I have my independent variable, that is uh, social media screen time, and then you have this happiness index, and it is ranging from 0 to 10. So you get multiple data points, like, so screen time is actually continuous variable. You are kind of discretizing it and then asking the questionnaire, like you are trying to get the amount of time people spend, or the 1000 people spent on social media, and the level of happiness they had, like through a questionnaire, and you would have got certain data points, like they spend so and so time. Well, this is not the case always. Let's say the data is like this, and based on this data you are trying to fit a line to find out the relation between the social media time, screen time, and the happiness. Say if the data were like this, so you can see that as the screen time is increasing, the level of happiness is decreasing. This is just an hypothetical example, not a real data, but say if it were like this. So in this case, with increasing social media screen time, your happiness is increasing. In this other case, if the data were like that, this shows as independent variable increases, the dependent variable decreases. And if it is like this, say the data was like this, evenly spread, so in that case it implies that there is no relationship between the social media screen time and the happiness. It is constant across all the subjects or people from whom you collected this data. Okay, so each of these lines will be having an equation y equal to mx plus c, that is a general equation of any line used in literature. And in this case, in the lecture you might be seeing this y equal to beta 1 x plus beta naught. So this beta 1 and beta naught are known as parameters of this line equation or regression model. Okay, so these are the estimates of the parameter, because in certain cases you might not be having all the data, like you are taking the data, in this case you are taking data from 1000 people, but there are like crores of people using social media around the world, and it is not feasible for you to like go around and get this data from each and every person. So you are taking a sample from the population and trying to predict a certain line on that, like a certain relationship between the social media screen time and happiness. So this particular line equation may or may not represent the actual relationship. So let's say the actual relation was beta 1 x plus beta. So this beta 1 and beta naught are the population parameters. So, like we had like mean in the case of a normal distribution, like we were having certain population and then we were having the mean and the standard deviation, assuming that the population was normally distributed. Okay, so in this case we are having the two parameters. These are the point estimates of those two parameters, beta 1 and beta naught. Beta 1 is the slope of the line. If it is positive, it means that the line is having positive slope, else negative. If it is negative the line will be having negative slope, and if it is 0, then there is no relationship between the y and the dependent variable, that is like y equal to some constant beta naught. Okay, so the task is to predict this and then see how significant. So we'll come on to the significance test for these parameters. So the first question is, how do we compute this b1 and b0? So we use this particular fact into consideration. A line will be a best fit for a given set of points if it minimizes the error between the points and the estimated values. What I mean by that, for every x value, you are let's say this is the x value, you are having corresponding y value over here, and you are trying to fit this line y equal to beta 1 x plus beta naught on this data point. Beta 1 and beta naught are b1 and b naught are unknown. Sorry for that, beta 1 and beta naught are like the population parameters, b1 and b naught are the computer statistics or the estimates that you are getting from the data. Okay, so this corresponding value will be let's say this is x1 y1, so this will be b1 x1 plus b0, this particular value over here. and this is your y1, and this is your error, also called residual. Okay, so the line which minimizes error across all the data points, for this data point, for this data point, for this data point, for this, and so on. So this particular error, whichever line minimizes this error, like the sum of all these errors, that line is the best fit for your data. Okay, so now once you have this, you can find out the relation between the two variables. You can find out, you can predict for an unknown value, like say this particular value over here, you can predict what will be the corresponding y value given the line equation. And then we'll move on to the later part. We'll see, like, we'll perform t test and f test on the computed line equation, the parameters, to identify the significance of each of those parameters. Okay, and then there are other terms involved. We'll come to that. One is coefficient of determination. Say you have been given data points and you don't know if there were no independent, you don't have the information about the independent variable, you just have these values given for y. So the random way, or how do you say, like a naive way to estimate value for the particular data points will be like just to take the mean of this y. Like you compute the mean of this particular data points. Say this is y1, y2, and so on. Y. So you compute the mean y bar. This is the naive way. So given any random x, you can just simply estimate this as y bar, like in a naive way, because you are not having this independent variable information. Now, given the independent variable information, that is x1, x2, and so on. Just ignore that naming convention here. So you have n data points, and now since this information is given to you, you will be able to fit a particular line to this data points. Okay. So without this independent variable information, you were having certain error. Okay, let me use some other color, this particular. So you will be having certain error over here without having this independent variable information into consideration. And once the independent variable information is given to you, you fit a line to it, you will be having certain error with respect to this line between the predicted value and the actual value. So these y's over here are the actual values. This is your independent variable, and for that independent variable you are predicting something. So this y bar was your naive prediction, and then this y hat is your prediction with respect to the line. So you can see that the error is getting reduced over here with respect to the naive prediction. Okay. So this particular error due to the line equation is known as sum of square due to regression, or y minus y bar square. sorry, just a second, the terminologies might be different in the let me just confirm the terminologies used over there in the slides. I'll just stop the share over here. Please excuse me for some time. I just want to confirm the terminologies used by Professor Ramesh for this terms. Okay, SSR, SSC and SST. Okay, so your SSR is, okay, I made a mistake. So SSR is the difference between your predicted one due to the regression and the naive prediction that you made. Okay, let me go back to iPad once. Okay, so this particular difference, the variance that is getting explained because of this introduction of independent variable and the naive like with respect to the naive prediction, this is your y bar, this is y cap, and let's say this x is over here. So this is your,
Excuse me, y hat. Yeah, okay.
yeah, my bad. So y hat minus y bar square. This is your error, or the error that is getting explained by your line equation. This is the total error that you have, and this is the residual, as we saw, y minus y hat square, and the total error is y minus y bar square. So this total error is equal to the sum of squares, or error due to regression, sum of squares due variance due to regression, and sum of square due to the residuals. Okay, so now if you divide it by SST, this will be 1 SSR by SST. So this particular term SSR by SST is called coefficient of determination. What does it represent? It says how much of the variance is explained after the introduction of that independent variable with respect to the total variance. So when in the naive case you are trying to predict, so when the independent variable was not there, you were having only the y values, so you are predicting everything as y bar. So this was the total error that you were getting, but with the introduction of independent variable, certain this particular error was getting reduced. between the predicted value and the actual value. Okay, so this particular part was getting explained, or the variance was getting explained by this particular line equation. So how much of the variance is getting explained with the introduction of the independent variable with respect to the total, with respect to the naive prediction that you were making. So that is given by coefficient of determination. So higher the coefficient of determination, what can you say about the error if r square? So r square can be written as 1 minus SSE by SST. So if r square is increasing, what can you say about error? That is the residual. The residual is nothing but actual value and the predicted value using the line equation. So this is your residual. So if r square is increasing, your residual will, the errors will, any answer?
Reduce.
Yes. So r square close to, so what will be the range of r square?
Plus minus 1.
Will it be minus 1? Like SSE is always less than equal to SS total. So this particular value over here will be less than equal to 1. So the value of r square will be between 0 and 1. And it is clear also, this is like a square term over here. This is sum of squares, the ratio of sum of squares, which will always be a positive value. Okay, so this particular thing will be between 0 and 1. So higher the value of r square, more is the variance in the data that is being explained by that particular line equation that is fit to the data. Okay, so let us go back, and there is one more term involved over here. We'll see it formally, like correlation coefficient or coefficient of correlation. So it is given by sine of b1 under root of r square. What it tells is the relationship between your independent variable and dependent variable, whether it is positively related or the negatively correlated. We'll come to that. First, let us see some questions and then we'll solve this. And we'll see these examples in Python. Okay, so here the answer was yes. Okay, so in a regression and correlation analysis, if r square value is 1, then what will be the answer over here? Okay, think over it, like what is the formula for r square? R square is, anyone?
Is it C?
Yes. So here the correct answer is SSR equal to SST, because R square is defined as SSR divided by SST. So how much of the variance is getting explained by regression, that is the line equation, and divided by the total sum of squares or the error that you are getting by naive prediction using y bar. So if this ratio is 1, it means that SSR is equal to SST. Okay, so this was a simple question. If the coefficient of determination is 0.81, the coefficient of correlation is
Is it B?
okay. What about the others?
Is it C?
Okay, let us see others. Please feel free to answer. It's not getting graded anyway, so you may guess as well.
Ranges from -1 to 1.
But you have been given a coefficient of determination. Yeah, correlation
It is
coefficient.
B. B only.
Okay, so let us see. So the correct answer is B. We just saw correlation coefficient is defined as, okay, let me go back to iPad. It is defined as sine of B. So you have this line equation, y equal to b1x plus b0. So correlation coefficient is nothing but your sine of b1 into root of r square, and r square value was given as 0.81. So if sine of b is positive plus, so it will be plus under root of 0.81, which will be 0.09, sorry 0.9, or if it were like sine of b is -1, negative, so it will be negative 0.81. So the answer is either plus 0.9 or negative 0.9. So what does correlation coefficient tell? So you have data points like this. And you fit a line. It means that, and y equal to, let us take one example, 4x plus 5. So this is the slope of the line, and this 5 represents the y-intercept, where the line is intersecting y-axis. So this is 5 and 4 is the slope of the line. So it means that for every increase in x, y value will increase by 4, factor of 4, ignoring the constant. So if x is 1, y will be like 20 approximately. If x is 1, it will be 4, if 2, it will be 8, and so on. So as x increases, y also increases. So this particular correlation is positive correlation, that is dependent on the sine of y or the slope of the line. If it were like negative, so as you increase x, y value is decreasing. So that relation between x and y is shown by the correlation coefficient. And you might also come across this formula for correlation coefficient: covariance of x and y upon variance of x. This is also this is the slope of the line, actually is given by this. And what is covariance of xy? There are two terms here, variance and covariance. So variance tell you the spread of the data in one dimensional space, or like given the data points, variance tells you how they are spread. So let's say this is a normal distribution. So this particular distribution over here is having more variance compared to this particular distribution. But now you are seeing the term over here is covariance. So it says how x and y are covarying. How is variance defined? Variance summation of xi minus x bar whole square divided by n minus 1. Okay, so forget about this particular part, the denominator. So variance is like approximately xi minus x bar square. Now, how do we define covariance? It is similar to how we compute variance, but here we are taking x minus x bar and y minus y bar. Again, it will be like divided by, summation will be divided by n minus 1, that is the degree of freedom, but we will ignore that for the time being. The covariance is approximately this. So what does this term mean? Say you have data point over here, let us see the Cartesian coordinate. Your data points are like this. Now you can see that there is a positive correlation over here, like as you increase x, y is also increasing, but to quantify that you will have to have certain measure. So in that case you are using this measure of covariance. So what you do, so these data points are having certain mean on the x axis and certain mean on the y axis. So when you subtract the mean of the data points, you are trying to shift the data points. Say I have these data points 2, 3 and 4. So what is the mean value of these 3 data points? It's 3, right? So when you do 2 minus 3, 3 minus 3 and 4 minus 3, you are trying to shift these points and make the mean 0. Similarly, on the y axis, when you subtract the mean from each of the data point, you are trying to shift them to have mean. So it's like this particular data points are getting shifted over here. Okay, so let's say these are the shifted values. Now what is x minus x bar? Let's say this is positive, right? And this is also positive. This is negative and this is negative. So x minus x bar and y minus y bar, this particular value will be positive when the data points will be lying in these quadrants, because here x minus x bar and y minus y bar is positive. In this case x minus x bar is negative and y minus y bar is negative. So negative and negative will become positive. So if the data is positively correlated, this particular product will also be positive if more and more data points are positively correlated. And if the data points are falling in these quadrants, one value will be positive and the other value will be negative. So this particular difference is positive and then this particular difference is negative. So positive into negative will be negative. So the overall summation of these differences will end up being negative. So that is the reason, that is the intuition behind that formula, covariance. So it is like how these two variables are covarying in the space. Okay, and that is given by x minus x, xi minus x bar, yi minus y bar divided by n minus 1 in general. So if you just divide it by the variance of x, there is a derivation for that, how this formula is derived. So you will have like covariance of xy divided by variance of x, giving you the slope of this particular line, whatever you are fitting in the on the data points. Okay, I hope you got the intuition behind this covariance term. It shows you how the two variables are varying in space. If they are, if one is increasing, other one is increasing or not, that is shown by the covariance. Okay, I hope it is clear to everyone. So the answer over here is could be either 0.9 or negative 0.9. Which one is better, r equal to 0.5 or r equal to 0.7?
B.
Okay, reason?
It shows that more of the graph under the this model is getting represented by the regression that we have created.
Yeah, so the term proper term over here is like more variance in the data is getting explained by the line equation that you are having. So that's why the sum of square due to regression is more, and hence r value is greater, like is better value. Like more is the r value, better is the fit to the data point. So answer is 0.7. Which of the following is possible for coefficient of determination?
Is it B?
Okay, what about the others?
First, one doubt is that is correlation coefficient and the slope are the same thing.
Correlation coefficient and slope, yeah, you can like they are not exactly the same thing, but means like you can consider them as like indicating the relationship between the two variables. Means, yeah. Okay, so the answer is we already saw r square will lie between,
B is answer.
yeah, it is less than 1, it will always be between 0 and 1.
Coefficient of determination will vary between -1 to 1, right?
It will be coefficient of determination is r square, it will be between 0
Oh,
and
okay.
1, and
Okay.
coefficient of correlation will be between -1 and 1.
Right.
Yeah. So let me show you the formula for correlation coefficient. So here correlation coefficient is given by variance of like covariance of xy upon variance of x, standard deviation of x into standard deviation of y, whereas the slope of the line is nothing but covariance of xy upon variance of x. So that is the only difference between correlation coefficient and the slope equation that you have.
Slope actually depends on the independent variable, but correlation coefficient depends on two.
On the two, yeah, that's
Yeah.
the thing. But the like the value, if it is positive, like it will be positive, like both correlation coefficient as well as slope will be positive if the two variables are positively correlated. So the sign will be the same. The only thing is the value is getting normalized with the standard deviation of y as well in the case of correlation coefficient. Okay. So the answer over here is it is less than 1. The interval estimate of the mean, okay, this is not covered yet. We'll skip this question for the time being. Okay, you conducted a mathematics test among 200 random children of school ABC. The mean score is observed to be 70 out of 100. There is a variability of 10 among the scores of the 200 students. Which of the following is correct? This is a quick question. We'll move on to the answer. Please quickly answer. We'll go to Python notebook.
C, 10 is the standard deviation.
Okay, what about the others? Okay, that's the right answer. So 10 is the standard deviation because this is the population, the information that you have been given, and 10 is the standard deviation for the population. Okay, if the two variables x and y have a strong linear relationship, then what is the answer? Okay, this is interesting question, so think over it. If two variables x and y have linear relationship, strong linear relationship,
That means they are correlated.
okay, they are correlated, that is true, but which one is the correct option over here? What do you think?
None of the above.
Okay, what about
Or
the
maybe
others?
there may or may not be causal relationship between x and y.
Okay, yeah, so let us see this example. Yeah, so the correct answer is A. There may or may not be any causal relationship between x and y, and let me explain it to you with an example. Say I have a scenario of certain tourism. So one data that is given to me is like as summer approaches, the sales of ice cream increases. So as summer is increasing, like as summer approaches or the temperature increases, and ice cream sales increases. Okay, now as summer approaches, the number of tourists on the beach, they also increase. Number of tourists on beach increase, and that leads to more number of sharks coming on the towards the beach. Okay, so summer is approaching, temperature is increasing, ice cream sale is increasing, temperature is increasing, number of tourists are coming on the beach, and the more number of sharks are coming on the beach. So now if you just plot this graph, ice cream sale and the number of sharks coming on the beach, it will be something like this. So as the ice cream sale is increasing, it means that as the ice cream sale is increasing, the number of sharks is also increasing. But is the ice cream sale causal for number of shark? No, right? So there is correlation in this data. There is strong linear correlation, but ice cream cell is not causing like increasing ice cream cell is not the causal relation for number of shacks. So there is a complete field of causality. So you will come across this. So I'm not sure if this is covered in the course, but this is like a recent trending topic in the research area, causality, where correlation does not imply causation. That is the main thing, and it is used in multiple research analysis, including so there is a friend of mine who is working on causal relations between the diseases and the expression of genes. So it's relating to bioinformatics, but yeah, if a certain gene is getting activated in your DNA in your body, so is that causal? Like if you are seeing the correlation, like if that gene is getting expressed and the disease is also occurring at the same time, is that particular gene causal for that disease or not? Is the expression of that gene causal for that particular disease? So that is the question that we are having. And then a friend of mine like tries to see this using some NLP based approach, like by doing an analysis of the literature, like the research papers that are published, and trying to see like if there is any causal relationship between genes and the diseases. So that is one example wherein the causality comes into picture. Yeah, there are more such examples. If you come across, you can also share it with others during one of these sessions. Yeah, so anyone having any query in this? Any query on this particular part?
No, nothing as of now.
Okay, great. So let us move ahead. Okay, this is also not covered yet, so I'll skip this part. Okay, multiple regression is also not covered yet. Okay, I think the rest of the questions are okay. Yeah, so this question can be answered. Ignore about the fact that there are two variables. Okay, so as x1 increases by 1 unit, holding x2 constant, y is expected to, a very quick answer.
Increase by 2 units.
Yep, so that's the straightforward answer. As x increases by 1 unit, y and x2 is constant, y increases by 2 units. Okay, so we'll come to statistical test, and then we'll move on to Python notebook, wherein you will solve these problems using Python. Okay, so let me go back, or I'll just explain it using the slides by Professor Ramesh. Let me just open that. So there are two tests that we can apply to see the statistical significance of the parameters. So as I said, beta 1, beta naught are the population parameter, and b1 and b naught is what we are estimating. These are the point estimates that we are estimating using the data we have. We may not be having the entire population data with us. So to test the significance of this particular regression that we have fit on the line that we have fit on the data, like how significant it is with respect to the population. So for that there are two statistical tests, t test and f test. We saw both of them. T test we saw for two times, like one sample t test and two sample t test, like independent t test, and f test we saw in the case of ANOVA. So let us see how this can be applied. So here there is the term standard error, which is again as we saw in the ANOVA, sum of squares due to error upon degree of freedom. So in this case, degrees of freedom is n minus 2. Now why it is there? So there is a reason, because we have one more term added over here, that is the number of independent variable. So in general, the degree of freedom in the case of regression, it is given by n minus 1 minus the number of independent variable. We'll see that in later slides. So the statistic that you will be computing over here is your b1, that is the point estimate for the slope, and then the standard error for b1. Now how is the standard error computed? This is nothing but the sample standard error, that is SSE by degree of freedom. This is nothing but the variance, and under root of variance, the square root of variance is your standard deviation. So this standard deviation is called standard error. For one sample t-test, it was population variance or sample variance divided by n and square root of that. So it was like sigma by root n. So in this case, you have the sample standard error, and you have this variance parameter term over here due to the independent variable. So this will give you the standard error for the regression slope coefficient, and the slope coefficient divided by the standard error will give you the t statistic with n minus 2 degree of freedom. Why n minus 2? Because there is one independent variable, so it will be n minus 1 minus 1, so that is n minus 2. Now why this is, like, we'll have a discussion on degrees of freedom later, like if it is not clear to you, but for the time being just keep this in mind. For k independent variable, if there are k independent variable in your line equation, variables in your line equation, so the degree of freedom for that will be n, which is the number of data points, minus k, the number of independent variable, minus 1. Okay, so given the t value, now you have the t statistic and you know the degrees of freedom n minus 2. So you can compute the p value based on that, given the level of significance. So here the assumption, the null hypothesis is that beta 1 is equal to 0, that is there is no relation between x and y. The slope term is 0, so no matter how much you increase x, there is no change in y, it will be constant. So that is our null hypothesis. An alternate hypothesis over here is beta 1 is not equal to 0, it can be less than 0 or greater than 0. So we are going to do two tail test over here. So for that we have two approaches: critical value approach. If the computed t value is less than minus t alpha by 2 or greater than t alpha by 2, we are going to reject our null hypothesis, or the corresponding p value, that is the area under the curve after t alpha by 2 and before t minus t alpha by 2, if that sum is less than alpha, we are going to reject the null hypothesis. This is t test. But in certain scenario, like in we'll come across multiple regression, as we saw in the case of ANOVA, like we were having multiple groups and we were trying to see like if they were different or not. So in that case we were not going for t test with every sample, every two pairs, to avoid this type 1 error getting accumulated. So in this case also, like in the case of multiple variables, independent variables, so we go for f test instead of t test for a similar reason. So f test can be applied for the two variables as well. Similarly, ANOVA can be applied for two groups as well. That is like a generalization of t test. So in this case the f statistic is computed. Let me show you. In the case of ANOVA, how was the f statistic computed? Anyone? What was f statistic? It was the ratio of two sum of squares, or the ratio of two variances. So what were those two variances? So there were three terms: SS treatment, SS error and SS total. Okay, so Soumitra says SS treatment by SSC, which is the correct thing. So sum up square due to treatment upon sum up square due to error. So in this case, your treatment is nothing but, okay, let me go back. Your sum of squares due to regression. So in this case, you are taking the mean sum of square due to regression, which is nothing but the variance due to regression and the variance due to the error, the residual error. Okay, so MSR is SSR divided by the degrees of freedom, that is a k independent variable over here, and as MSE is nothing but sum of square due to error divided by the degrees of freedom. So here it is n minus k minus 1, so it will be n minus 1 minus 1. We have one independent variable, it will be 2. So SSR by 2 upon SSE by n minus 2. That will be your F statistic. And then similarly, like as we did in ANOVA, based on the F alpha given label of significance, you will compute F alpha. If F is greater than or equal to F alpha, you will reject null hypothesis or the area under the curve for this particular F. If it is less than alpha, then you will end up rejecting your null hypothesis. So this is the overall overview of that, and let us now see this how we can solve this in Python. Okay, so let me connect this. By the way, I'll be sharing all this with you. So the data files that I am using over here, these are available in week 6 important data link. So in week 6 you can go over here, important data files, and you will find it over here in this drive folder. So they have shared some drive folder over link over here. So all these data files are here, Excel files. Okay, so I'm importing all the necessary libraries. We'll see one by one. So scipy.stats. Okay, one query. I think Akhilesh ji, you had a query like what is the internal implementations of these libraries, right? So
Right.
yeah, so you can find all these files on GitHub as well. So if you just see scipy GitHub. So GitHub is a online platform where where you the researchers put in their work for open source development. Like if you are developing certain software, you can put it on GitHub, and others can use that particular code and make changes to it and develop their own softwares. So it is like you are making your codes publicly available. So for that GitHub is used, and it is a version control platform. So it's like you can code on your system and then kind of like log it to the GitHub repository. So you create a repository over here, and whatever code you write, you'll keep on logging it over here. So you can see the different versions also for your particular code. So you can see there were multiple commits over here. So you can see different commits at different times, like the bug was fixed and then certain part was cleared, and like as you improve your code, like kind of fix the bugs, those will also be getting reflected over here in the version history. So if you go to the go to this scipy's GitHub repository, you will see scipy over here, a folder called scipy, and in that there is this subfolder called stats, and in stats you will be having multiple Python files, like for example distributions.py. So it is a bit complicated, like all this there are multiple Python files, and there will be one particular file that will be accessing all these Python files. So you need not go into the details of that, but you can see all the implementation, like how the hypothesis testing and other things are implemented internally. So you can see all these things over here, but if you are not knowing the object oriented programming concepts in Python, it will be a bit difficult for you to understand that. But yeah, if you are curious to know, you can definitely go to any like Python libraries GitHub repository and then look into that. So this is for SciPy. There is one more library in Python, very popular library called TensorFlow, which is used for machine learning purposes, like especially for deep learning models. So you can also like go to the TensorFlow repository for on GitHub and then explore the things over there, like how these people have coded that. So anytime you feel like looking into the internal implementation of these libraries, you can go to the GitHub repositories of the same. Okay, so coming back to the notebook, so we are importing stats from SciPy. NumPy is getting imported. Math and all, I think we are not using math as such in this particular example. Pandas we are importing for reading the Excel files and storing the data in a data frame. SciPy, this is not needed as such, I'll remove it. Statsmodel.api as SM, this is used for linear regression tasks. Again, the statsmodel formula API OLS, this OLS stands for ordinary least square. So again, as we saw in ANOVA, it will always it will also be used in the linear regression task. And matplotlib.pyplot, this is a matplotlib is a library used for plotting purposes, and PLT is an alias for this particular. In general, we use PLT for matplotlib.pyplot. You can give, as I said in many of the previous sessions, you can give any name you prefer, but PLT is a general notation that is used for that. Then Seaborn is again a library for plotting purposes, and anytime you feel like stuck with any of the libraries, you can just go to the documentation of the library and get a hold of it, like how to install, like there will be a tutorial and all for plotting purposes, so you can go and look into that. And if you are stuck with any particular thing, if you are getting an error that something is not defined or some I'll show you an example. So you can simply search that error, and there are forums like Stack Overflow and other things. So you can go over there and look into the solutions given by the community. So Stack Overflow is one such community. There is Math Exchange or Stack Exchange. There are multiple such forums wherein you can put on your query, and you can also look into the queries of others. Like if somebody else has already put that query that you also are having, you can see the solutions over there, like the answers given by other people in the community, and you can get you can resolve your queries accordingly. Okay, so let us go over here. Seaborn, matplotlib as MP. So these are like just given just for example. We may not be using all of these in the in these examples whatever we are seeing, but just for your knowledge, like what all packages we can use. So first of all, this is two-way ANOVA. I'll skip this part, we saw this already in the previous session, but let me just quickly show you like how it was working. So we were reading the data from the Excel file, and then in the two-way ANOVA we were having this so there was one dependent variable and two independent variable. Like in the example that we saw for two-way ANOVA, there was this preparation program and the college that a particular person was having. Based on that, like there was a certain CAT score. So the task was to identify the significance of each of the independent variable for this particular score, if it is important or not. So in that case, we were treating it as a linear or a regression ordinary least square problem, wherein the value was dependent on this categorical variable. We will see categorical variable later. So it was dependent on college, the preparation program, and the interaction of college and preparation program. So you wanted to see like which one is significant, if the college is significant or the preparation program you are taking for the CAT preparation, it's significant, or the interaction of both the things, the background you have and the preparation that you are doing. So in this case you are getting a certain p value for each of these particular independent variables, say college, preparation program, and based on that you are deciding if a particular independent variable is significant or not. So in this case it says that the college is the background, the graduate level background you have is very significant in deciding the CAT score, but the preparation program and the interaction of the background and the preparation program is not so significant if the level of significance is 5%. So this was in the case of two-way ANOVA. Here in linear regression you are trying to find, so you have been given one independent variable and a dependent variable. So I am reading this data from regression.xlsx, and let us plot this over here. So I am reading this data in this data frame. This is the data frame. It is having two columns, TV ads and cars sold. It is already given, like you can also give names to the columns, but we are using them as it is. So data.plot, data.columns. Let me just print data.columns over here. So it will be a list of the columns present in the particular data frame. Okay, column names. So data.columns0 will give me the first column name, data.columns1 will give me the second column name. So I am plotting this x and the y value, and this style equal to 0, it represents what kind of style I want like this particular data points to be in. So if I say star over here, asterisk, so I'll get asterisk over here on the plot. If I say like let's say plus, so the data points will appear like plus. Okay, so this style is, so there are multiple other things in this plot. So if you just go to data frame plot, documentation, you will see other things as well over here, and you can explore it later, but for our information this is the simple thing that we are doing. We are plotting x versus y, the independent variable versus the dependent variable you are giving. So this PLT is your object, the library, alias for the matplotlib library. Your figure is getting created with this. Internally it is using, the data frames is using, pandas is using matplotlib library to plot this. In general, like if you are plotting something, we generally like give this initialization for the figure. You might be seeing somewhere like this plt.figure. So it kind of initializes a blank figure, and then for that blank figure you give this particular values like x label, y label and title. So x label will give you the x label, y label will add the y label over here, and title will add a title to this particular plot. Now question, I think Akhilesh, you had a question like how to save this particular plot generated on your local system. So there is a function in PLT matplotlib, save fig. I think save or savefig. Let us see if savefig works. So you can save it as sample.png. Okay, so let us see if it is here. Yeah, so the sample.png got saved over here. But okay, there is one more thing. You will have to, in certain thing in your local system, you will have to have this particular comment or command plt.show. Let us see. Okay, somehow it is becoming blank over here. I'll figure that issue out. But the thing over here is, if you want to save a figure, you can use this plt.savefig and provide a path to your directory. So if your path is like, if you have a folder in C directory in C drive, you'll have to have like desktop and so on, your folder name. So you'll have to give the complete path if you want to store it in some other directory, and if you want to store it in the same directory as you are working in, you can simply give plt.savefig and the file name as a string to the function savefig, so it will save the figure over there. I'll have to figure this out, like for a particular figure generated by this data frame, why it is turning out to be a blank one. Let me just download it and see if it is. Okay, yeah, I'll just figure this issue out, but yeah, you'll have to use this plt.savefig function to save your output. Oh, okay, I hope that clarifies your query, Akhilesh ji.
Okay.
Yeah. Any other query relating to that same thing? Okay, so let us move ahead. Yeah, so I'm having this TV ads. Now, given this data frame, I'm getting the data for this TV ads in one particular list called TV ads, and getting data for cars sold in the second list. Now I want to fit this linear regression model on this particular data points that we have. So we have x and we have y values. So first of all, what we are doing, sm.add constant to TV. So why is this constant being added? Let me just show you how it looks. So you have your TV ads, you have the corresponding car sold value, the number of sales of car, and let me just run this once and print this TV ads here. So first TV ads are having like only 1, 3, 2 these values, and let me print this TV ads now. Okay, so you can see one constant is getting added over here. So the reason being, internally it does some linear algebraic operations like matrix multiplication and so on, and for that purpose you use this constant for the intercept term. So that constant is added just for the internal computation of the OLS sm.ols function, if you are having this intercept term as well in your line equation. Okay, so let us see the later part. So you are having this stats model.api, you are importing it as sm, and it is having this OLS function. Okay, where it is. Yeah, so it is having this OLS ordinary least square function implemented in it. You are passing the y value, that is the car sold, and the TV ads, but with an added constant over here. And then once you get that model, you fit the data on top of it. So model.fit will simply do the internal computation. You are like triggering that particular computation with this model.fit, and the result is getting stored in this particular variable called result, and result.summary will print the complete result that you are getting. So here constant, after computing the values, you are getting the constant, the y-intercept as 10, the slope for TV ads as 5, and you can see the r square value over here, which is nothing but your MSR or SSR by SST. We'll see what this adjusted R square is in multiple regression case. Then you will be seeing you can see F statistic and the T statistics over here, which show the significance of each of the parameters that you are computing. So B0 is the constant parameter and B1 is your slope, TV ads, the coefficient of TV ads, and F statistic is over here, which is nothing but the ratio of the regression, sum of square due to regression and sum of square due to error. Okay, so based on that you will get a p value corresponding to F statistic, and you will get a p value. You have this individual p value for each of this so this is like overall significance of the regression model, and this is like significance of individual data, like individual parameters you have in the regression. So in case of multiple regression, you will see that when you have multiple independent variable, for each of the independent variable you will have a corresponding t value and the p value. Based on that you can see if it is statistically significant or not given a level of significance. Okay, for the time being you can ignore all this other terms. These are not of our use right off as of now with respect to this course, but you can explore it in detail later if you are interested in that. Okay, so let us see one more example over here. So I'm reading this another data, so which is having a hydrocarbon level and the oxygen level. Okay, so let me just show try saving this.
Try saving before the command plt.show.
We'll have to do it before after it only. Sorry, who was it? Okay, let me try to do that. Okay, it worked. Okay, thanks for that. Like I never tried that out.
Actually, that plt.show
Will display.
releases it and creates a new image, and then you can start.
Yes, exactly. So yeah, so Akhilesh ji, that resolves the error. So you will have to save it fig and provide the path over here to your directory where you want to save the fig and the file name as well.
Thank you for that.
Yeah, and thank you. I think it was Nikhil, like, so for the help. Any query? Yeah, Revent, I'll be sharing this with you. Like this particular notebooks and the slides will be shared in the drive that I have. So you can go to my YouTube channel and you will find a link over here below in the description. So if you visit this link, you will find all the material that I'm using for the sessions. So if you go to a particular week, you will find a link to the Colab notebook as well as the slides I have used for that particular week. So you can create a copy of this Colab notebook and edit it yourself. Like you can play around with it later. Okay. Yeah, so in this case it is just for the plotting purpose actually, like you are having this X value hydrocarbon level. Okay, let me just print the data as well here. The hydrocarbon level and the oxygen level. So you're trying to see as the hydrocarbon level increases, how much is the level of oxygen for a particular level of hydrocarbon. So I'm taking this independent variable in x, dependent variable in y, and as I mentioned, like we are creating a figure, instance of a figure with plt.figure, and then this Seaborn is one of the libraries that is used for plotting purposes. Okay, so in the lecture slides, you might be seeing this particular parameter which is now deprecated. So fit reg equal to true, it was given by Professor Ramesh. If you try to do this, it will throw you an error. Okay, let me just say, like he mentioned it like this. So it will just throw an error that rec plot takes 0 to 1 positional arguments if you don't clearly mention. And if the reason was, let me just, that was like the older version of the library. So this is one problem with Python libraries, like their versions, like the of each of these libraries get like you'll keep on getting newer versions of these libraries, and many of them are not backward compatible. Like the definitions that they may be having or the requirements they may be having for the current version may not be the same as what they were having for the previous version. So you'll have to be like clear with that, and then go to the documentation of that particular version and see the way you have to give the inputs. So this is Seaborn dot regression plot like function, and you can see the parameters it expects over here, like kind of parameters that are available in this particular function. So you will have to look into that and then accordingly work. So in this particular environment, collab environment, it is using the latest version of sns.regplot. So you'll have to take care of that. So either you give this parameters as like this, but this is by default true and that, so you need not give that as well. So yeah, you will have to look into the documentation if you come across such an error. Okay, so then we are like so we have fit a regression using this snet.rec plot, and then we are having this scatter plot of the mean value. So you are computing the mean of the independent variables and the mean of the dependent variable, and plotting this as a green point over here. So this was just to show that this line, the base fit that you are getting, it always passes through the mean of the x and the y values. So whatever x values you have, data points, and the y values, the base fit line will always pass through the mean of these two data. Okay, that was the only aim to plot that over there. And let us see one more example. So here you are having this ice cream sales and the student population as it is increasing. You are having this x value, y value, you are adding constant to it for the internal computation and passing this variables, the dependent and the independent variable, to the OLS function, and then you are fitting the model on top of the data and getting the summary over here. So you will get the constant. So the line equation will be 5x plus 60, and you will get the corresponding p-value. So here the p-value is quite small, that's why it is being displayed as 0.000. So it is less than that in the sense like 0.00, it might be 0.001 or so on. So the precision value over here is only 3 decimals, so it's not exactly 0, it is greater than 0 but quite small in magnitude. and you will be getting the r square value over here. So you can see that the r square is pretty high, which means that the particular line equation that you are getting, it is capturing maximum variance in the data. You will be getting the corresponding f value and the p value for this particular f statistic. So you can see that. So this particular notation, for those of you who are not aware of this, so it is e to the power 0.5, it's like 2.55 into 10 to the power minus 5. So it's like 0.00001 into 2.55. Okay, so this was all about the regression. We will see multiple regression in the next class, and I'll also cover maximum likelihood estimation and logistic regression if possible. So are there any queries on the topics that we have seen so far?
Just one, I want to know, in this our TV ad and car sales,
Okay.
if I want to do optimization of the TV ad, then for that I have to make another regression model, or same we can do some modification in that.
You mean you want to make it better, like with more data?
For optimization of the TV ads.
Optimization of TV ads. Sorry, I think I didn't get your question clearly.
No, optimization, I mean the expenditure which I am incurring on the TV ad and then what profit I am getting out of sale.
Okay.
So that optimization.
Oh, you mean you want to add one more variable to it, that is the cost spent on the
TV ads.
TV ads. Yeah.
Yeah,
So
and then
we'll see
profit
that.
which I am getting out of the sale.
Yeah. So that comes under the purview of multiple regression, multiple linear regression, wherein we have multiple independent variables. So but in this case, the cost that is getting incurred for TV ads, it's not an independent variable as such. So we'll look into it, this problem, in the next session, Akhilesh.
Okay.
Sure thing, Saish. Thank you.
Sure. So thank you everyone for joining the session, and yeah, please let me know like if you have any queries, and also if I have made any mistakes, so please let me know that also in the next session. I'll be happy to correct myself. So thank you.
Thank you, sir.
Thank you for the session.
Thank you, sir.
Thank you. Yes, anyone having any query? Okay, so I'll end this session over here. Thank you.
Yeah, thank you.